Alright, section 1.4. The matrix equation AX equals B. Now this equation is one that we're going to spend a lot of time on this semester, and this section is going to be a key section, so make sure you read the section carefully. So AX equal to B is the same as asking yourself, can I write the columns of A as a linear combination, in a linear combination to equal B? And that's the same as looking at the augmented matrix with columns A1 through AN and B. So we can ask, is B in the span of A1 through AN? And that's similar to asking, is AX equal to B consistent? Okay, so is that question consistent? And again, that's similar to looking at this augmented matrix here. So when we have these questions, we're going to couch it in terms of thinking about the augmented matrix. So just to make sure we're okay with working with this, let's write this linear combination of vectors as a matrix equation. So I'm going to make a coefficient matrix here that has the two vectors, and then multiplied by the vector 2, 4, and that's going to be equal to 6, 6. Alright, so that makes a matrix equation. You want to get comfortable with switching back and forth between the matrix equation and the linear combination and the augmented matrix. Alright, so theorem 4 is the big theorem in this section. So let's suppose that A is an n by n matrix, then the following are equivalent. So part A, for each B in Rm, AX equal to B has a solution. So for any B in Rm. That's the same as each B in Rm is a linear combination of the columns of A. And that's the same as saying the columns of A span Rm. So what does that mean to span Rm? That means that any vector in Rm can be written as a linear combination of the columns of A. And this last condition is equivalent to the previous three. A has a pivot position in every row. Alright, so a pivot position in every row. That means if you were to think about writing, can I find X such that AX equals B? Well, to be able to do that for any B, that would mean when I look at the augmented matrix with the columns of A and then B, I would need a pivot position in every row, okay, to have a unique solution for every B. And so that's where this last condition is coming from. Again, this is a really important theorem. We're going to be using it a lot this semester, so make sure that you work with it and that you're comfortable with it. Alright, so let's use the theorem to look at an example. So consider A is the matrix 1, 3, 0, 3, negative 1, negative 1, 1, and so on. Can each vector in R4 be written as a linear combination of the columns of A? Do the columns of A span R4? Alright, so this is the question. This is equivalent to asking, is there a pivot position in each row of A? And that comes from part 4 of the theorem. Remember the 4 things that were equivalent. If there's a pivot position in every row of A, then that means that the columns of A are going to span R4. Alright, so what do I need to do? I need to put A into reduced row echelon form. And I'm not going to do the calculation for you, but here it is. And so, is there a pivot position in every row? Well, there's a pivot here, and there's a pivot here, and there's a pivot here. But row 4 does not have a pivot position. So what can we conclude? Well, we can conclude that no, we can't span R4 with the vectors in A. All right, we can't write each vector as a linear combination of the columns of A. So the columns do not span A. Now I'd like you to think about, can you come up with a matrix that would, the columns do not span A. Oh no. The columns do not span R4. Sorry. Let's just say R4. Columns of A. Can you think of a matrix A that would span R4? So find a matrix A, oops, whose columns would span R4. Well, this should be easy. According to Theorem 4, all I need to find is a matrix that has a pivot position in every row, and so any upper triangular or lower triangular matrix would do. And in fact, probably the easiest one is the identity matrix. Here. And it's easy to see that this is going to span R4. Any vector x1, x2, x3, x4 in R4 can be written as x1 times 1, 0, 0, 0 plus x2 times 0, 1, 0, 0 plus x3 times 0, 0, 1, 0 plus x4 times 0, 0, 0, 1. Okay, so clearly this is going to span R4. However, not every matrix we're given is in such a simple form. All right, please work with this theorem, work in these sections, and email me or talk to me in class if you have questions.